lab, which is the pre-skills one, is due on the day of the experiment. And again, that's through Cengage. And I only made it due till next week again, so you could get a chance to get your OWL all in order. Looks like a lot of you already logged on to OWL and all that. And then every lab that we do that's an experiment, again, not the ones that are activities or anything like that, those will also include a pre-lab that you write. Again, like it says in the syllabus, you write the procedure. Again, you could do it either as in your own words, the actual procedure, not copying exactly word for word what's in the lab manual, because I already have it. I don't need that. Or you can do some type of flow chart, some way to, you know, kind of do a flow chart sort of the procedure. Again, it's just to make sure hopefully that you read the experiment, you have an idea what's going on in terms of the experiment that we're going to kind of do that day. So there is technically kind of 2 pre-labs that are due, and starting next week, both will be due at the same time at the start of the experiment, basically, or 10:30 in the morning, start a lecture, but on the same day of the experiment. So if you haven't done the pre-lab for today's online pre-lab, the OWL part through Cengage, which is that pre-lab skills, that one will be due on Monday, along with Monday's experiments. Pre-lab will be due online as well. And then you will also have the written experiment procedure that will be due for each of those. So obviously the written one will be uploaded on the Canvas site in the modules. There's a cell that's for each of those experiments that says pre-lab, and that's where you'll upload it. And then obviously you need to go to Cengage to do the Cengage part of it. Any questions on any of that there? All right. So like I said before, we are doing experiment 2 today. So since the first day was mainly spent kind of working on the syllabus and a little bit of chapter 1, we're going to continue on lecturing here for just a little bit of the time here in lab, and I hope it will get us through the information that you need for the lab that we're doing today. And then we'll do the lab and watch the video and continue on, obviously, and all that. I don't know if I have the answers to the practice worksheet. Again, there is a worksheet in that first module, which I think is about significant figures. As of now, it's not going to be turned in or anything like that, so I think it will just be practice. I have to check and see if I do have the answers to that particular one. All right. Any other questions on anything there before we start? Okay, so again, looks like most of you did, but again, remember to put here in the chat box for the roll. And if you do have questions, make sure you answer it. And again, I hope it looks all right on your screen. It's big size, I hope, yes. All right. Okay. So we're just going to kind of continue on just to get through, hopefully, the material that definitely you'll need to sort of make sure that you can complete the lab sort of correctly and all that good stuff. So we've been talking about taking measurements and the proper way to take measurements. And again, the idea of recording all the certain digits plus that first uncertain digit. And as we've been talking about, that really is what makes up significant figures. So again, in this particular example here, as we see 2.76, if we were given that as a measurement, we would assume in this case that these first 2 numbers here would be our certain number. The last number here would be our estimated or uncertain number. And taking all of those things together would tell us that it has 3 significant figures in this particular case, with the uncertainty falling in that last significant figure, which is the 6 in this case. And that's also something to be important to remember as we go through this. A lot of times the uncertain number is the last number in the measurement, but it may not always be the actual last number. It's actually the last significant figure that you have in a measurement. So the uncertainty lies in that last significant figure, which in 9 times out of 10 cases is the last number, but doesn't always have to be a last number. We'll see an example of that as we get going through here. In this case, the uncertainty is that last digit, and again, it could be as big as that or as small as that, kind of up or down one of those guys. And again, here we take a look at a volume reading. And as we talked about, we always want to read at the bottom of that curvature, of the bottom of the meniscus, Again, in certain pieces of glassware is a lot easier to see. You could really see that kind of curve. Other cases, you know, depending on it, you can't really see it. It's kind of, you know, not as defined and stuff like that. But you should always try to look for it. And again, as we talked about, always from the bottom of the meniscus is where you want to take that reading. So again, here, if we just look at the scale from say here to here, that's 40, that's 50. And again, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings between 40 and 50. That means in this case, each marking is 1 milliliter, right? And that means that if we divide that by 2, we could take it to the first decimal place, which is, you know, that point something. And if we look at here at the bottom of the meniscus, again, this is 30. This would be 31, 32, 33, 34, 35, 36. And again, it's definitely above 36, hopefully. So that we would record 36. And again, because we have that ability to do so, we would take it to the next digit, one more place to the right. And in this case, they went with 36.8 as their reading here. Again, certain numbers here, first uncertain number right there, and altogether this would have 3 significant figures. And it would, uncertain digit in this case, again, would be that 8. The reason, as we were talking about at the very, very end there, you just don't want to cut off digits is if you just went, hey, I think it's 36. What this would imply, if you gave this as your reading, this would imply that this number has only 2 significant figures. And it would imply that the 3 is the certain digit here, the 6 is the uncertain digit, which means that reading could be something as big as like 37, could be as something as small as 35. And you can see 35 is like way down here. You can see it's nowhere near the 35 mark. So by lopping off that extra digit that you should have recorded, you've just made your measurement really crappy, to be honest with you, right? So you're really, really off in terms of that. So it's really important not to just lop off digits, to look at the equipment and make sure that you do take it to the proper reading, because when you're doing that, you're ruining how good of a measurement you can actually take. Now, when we use something like a Buret, which is a common piece of equipment in the chemistry lab, the scale is actually a little bit different. If you look at the scale here, and I kind of blew it up here, that's 28, and this is 29. So in a Buret, the liquid comes out the bottom. Yeah, you fill it from the top. And basically, as you open it, it will drop out the bottom. So we're actually losing volume. At the very top of a Buret would be 0. And then it goes 1, 2, and so forth all the way down. Now, when we would take a reading of something like this, this was the meniscus, say here, it is actually above the 29, which means this would be 28 point something and not 29. So sometimes people read it the wrong way. Again, when you fill it from the top, empty it from the bottom, you got to make sure that you read it the correct way. And as you can see here, this is 28.85. And that is because if we look between 28 and 29, again, there are 10 markings, which means each marking here is 0.1 milliliters divided by 2. Gets you to our precision here, right, of 0.05. Also tells us that we should take this reading to the second decimal place. And that's, again, why we got our 28.85 milliliters. Here, we would assume that these first 3 guys here would be our certain digit. This would be our first uncertain digit there. And again, this particular number would have 4 significant figures in that particular case. So sometimes glassware doesn't always, you know, kind of increase as you go up. It, you know, can decrease as you come down. So you want to make sure that you do read it right. So very common people will screw this up. The other very common thing people will do with the Buret is, again, I'll just draw the top is 0, bottom is 50, and they'll record, if they fill it all the way to the top, they'll record 50, which is incorrect. And they should record, obviously, if you filled it to the top, 0.00, which again is a very common mistake, especially with something like a Buret, which is used. So why don't you take a second here and figure out which one it should be based on what you see. Okay, so if we look at this here, we got 10, for example, and we got 20. So again, that is 10 milliliters. And there are 10 markings in between each of those. And that means that each marking in this case is actually 1 milliliter. This would be 11, 12, 13, all the way down to 20. So if we look at our meniscus, which is down in this region, it is below the 20, so it should be 20 point something. And we want to see about where it's at. We definitely know that we can then divide this by 2 and go to the first decimal place. So that should eliminate this guy. That should eliminate that guy. And that should eliminate that guy and this guy as well, which means we should end up as something like 22.0. And again, well, it may be hard to see, but it's somewhere around that second dash. Again, may not be exactly at that second dash, and we do have the ability to go here. So also important that if you do feel it is exactly at a perfect line or something like that, you do need to record that extra 0 if it is possible to do so. And in this case, you would, and this would have 3 significant figures in this particular case. Any questions on that reading there? And again, it is 20 point something, 20 something, not 30 something. Again, reading from the top down because that's where the 0 is. Any questions on that? Okay. So we talked about significant figures, and let's just kind of get to the rules of those guys. But this is pretty much what we've been talking about. Again, because we record all those certain numbers plus that uncertain number, that is where our significant figures lies. And again, that uncertainty, as a reminder, lies in the last significant figure, not necessarily always the last number in a measurement that you take. So let's talk about the actual rules for counting significant figures. The first one's pretty simple. All non-zeros are significant. And usually if you look at a number, you want to go left to right, starting with the very first non-zero. That's when you should start counting. And anything that is obviously a non-zero is always going to be significant. So looking at our first number here, starting to count here, that is 1, 2, 3, 4 significant figures. Our next number, 12.5, looking over here, that is our first non-zero. So that is 1, 2, and 3 significant figures. Coming over here, our 4 is our first significant figure. So we will go 1, 2, 3, 4, and 5. And again, since all these are non-zeros, they're all going to be significant. And again, that's why we got the 4 significant figures, 3 significant figures, and the 5. So it's really important in terms of that non-zero is, in addition to them being significant, left to right on the number, when you hit the very first non-zero, that's when you should start counting. Again, you shouldn't count until you hit that first non-zero. And that's because of the zeros. There's 3 different types of zeros that we come across when we're looking at significant figures. And the first type is a leading zero. And these are all the zeros that basically come before that first non-zero number. And those are never significant. So when we look at this number here, start left to right, we don't hit that first non-zero to right there at the 4. The 4 and the 8 then would be 2 significant figures, those zeros kind of placeholders, if you will. All these zeros here are not significant until we hit the very first non-zero, which would be the 5. So 5, 4, 3, there is 3 significant figures. These are not 0. And that there would be our first non-zero, which would be 1 significant figure. So you could have as many zeros as you want that comes before the first non-zero. They're not going to be significant. And that's when you should start counting, is when you hit that very first non-zero number. Now we have zeros that come between 2 non-zero numbers, and those are always going to be significant. So sandwich numbers, captive zeros are sometimes called. So coming at this number here, this is our first non-zero. So we start counting. So significant, significant. 0 is trapped between 2 non-zeros, significant and significant. So that would get us our 4 significant figures. Starting here, this is our first significant figure. Again, these are all zeros that are trapped. So they're all going to be significant. And our guy at the end there will also be significant. So 2, 4, and 5 significant figures. Again, all these zeros are leading zeros, not going to be significant. We start counting right here at the 4. The 0 is trapped between two non-zeros, and that will be significant and significant, which would give us our 3 significant figures. Any question on that one? So zeros before non-zeros, not significant. Zeros between two non-zero numbers are significant. And the last type of zero that really messes with people is the trailing zeros. So these are the zeros that come at the end of a number. And they can be significant. They may not be significant. And what really determines whether or not the 0 at the end is significant is there a decimal point in the number? The decimal point does not have to be next to the 0. It just needs to be somewhere in that number for it to be significant. So when we look at this here, we have our starting to count here at the 9. So that is 1. The 3 is 2. These are zeros that come at the end. They are significant because of the 0 that is there. And that is why it would have 4 significant figures in this case. Coming to our 150, this is significant, starting to count. This is significant. This is a 0 that's at the end, does not have a decimal point in it, so it would have 2 significant figures. I'll get to your question in 1 second on that. And let's take a look here at this one. Here is zeros that come before the non-zero, so they're not significant. We would start counting here. That is significant. The 0 between the 9 is significant. The 9 is significant. This 0 here is also significant because of the decimal point, and it would have 4 significant figures. So your question was 20.00. This we would start counting here at the 2, which would be significant. And then technically all these zeros are trailing zeros. They're all the zeros come at the end of the number. There's not another non-zero in sight, and they would be significant because of the decimal point here. This would have 4 significant figures, as you see there. Yeah. So those zeros really, are what give people a hard time. So for example, again, the importance of that is 150. And if you wrote 150 with a decimal point there, yeah? This number here, as we just talked about, would have 2 significant figures. This number here would actually have 3 significant figures. And with no 0 here, the uncertain number is actually the 5 is the uncertain number. While when we put the decimal point here, that makes this significant, the uncertainty here is in that 0. So this is an example of what I was talking about earlier. The 150 with no decimal point, the 5 is significant, but that is where the uncertainty lies, not in the last 0, but here it does lie in that last 0 because that last 0 is significant. And the difference here is in the first one, that number could be like 160 or 140, as big as 160 or 140. While when we look at the second one, that may be like 151 or like 149. So a much better measurement here, right? Because we made this significant, a much bigger sense of sort of error between those. So let me just grab some of these. So, so a number like 5,000, which I think is what we got going there, number like 5,000 written just like this would have only 1 significant figure, which means both the certain number and the uncertain number is basically here. And that basically is not a great measurement, because basically what you're talking about is it could be as big as like 6,000, right? And it might be as small as like 4,000, right? That's a pretty big area of where the actual number may be. Now, if you put the decimal point on at the end, it would then have 4 significant figures. And the uncertain number would be here. The uncertain number in this guy would be here at the first one. You can, if you're asking, can you write it with just a decimal without the 0? You can. And what that would imply is that the uncertain number is here in like the first ones place. If you put the 0, the uncertain number would move to the first decimal place. So again, it's really important, the decimal, and also whether or not they do write the 0 or not, because again, putting the 0 after the decimal place moves the uncertainty to that digit. Without it is the ones place versus the tens place. I think I got everybody's question there, I hope, yeah. So again, when we do record a measurement, we're looking for all the certain numbers plus that first uncertain number. And again, that is basically what represents our significant figures. And the importance of significant figures is it really does tell you how good or bad, for example, a measurement is and where sort of the uncertainty lies. You know, if you had somebody come measure something for you and they go, I think it's 5,000, no decimal there. And it's like, well, could be 5,000, but maybe it's as big as 6,000 or 4,000, depending on what you're buying. As opposed to if you did put the decimal there, you know that it's within, say, if these were feet, within 1 foot of 5,000, you know, his measurement, it was that good. As opposed to here, he was within 1,000 feet of the measurement itself in terms of the uncertainty. So the significant figures really does play a big role in letting somebody know how sort of good or bad a measurement is, or how precise a measurement is, right? So if somebody was measuring something for you, you would want them to get pretty darn close to the square footage, right, you're buying, as opposed to like, it could be, you know, as big as a couple of thousand difference between them. That is exactly right. So in terms of writing significant figures, there may be only one way to write something with the correct number of significant figures, and that way is to use scientific notation. There is a difference between 50 point and 50.0. So for example, 50 and 50.0. This number would have 2 significant figures, certain number, uncertain number. This number here would have 3 significant figures, certain number, uncertain number here. In terms of quality of the measurement, this guy here, the uncertainty is in the ones place. In this measurement, you were able to get the uncertainty down to the tens place, which is much better measurement if you want to think about it that way. Other questions on that? Okay. So if we take a look at this number here, and we want to know how many significant figures there are, this is 1 significant figure when we start counting. Again, these are leading zeros, so we're not going to worry about them. This 0 is trapped, so it's significant. This 4 is significant. This 0 at the end is significant because there is a decimal place. So again, does not have to be right next to it or anything like that. So the correct answer here would be 4 significant figures in this particular case. Yes, I believe that is correct. So if you just wrote 50, no decimal, the uncertainty would be in the 10th place, which means, again, it could be as big as 60, could be like 40. If you wrote 50 point nothing, that would be in the ones place, which means it's got better, the measurement. It could be like 51, maybe 49. And if you went to 50.0, got even better the measurement, it means it could be as, you know, 50.1 or 49.9, you know, in terms of the uncertainty. Yeah. All right. Now, there are some numbers which are considered exact numbers. So exact numbers are pretty much 2 things. They're either definitions or things that are counted. So 1 inch is equal to 2.54 centimeters is an equality. It's a definition. And that's an exact number. 1 pound is 453.6 grams, 12 inches in a foot. Those are all equalities and definitions. They're basically 2 things that represent the same amount of something, but are on different units. and those are what are considered exact numbers. Another way you get an exact number is by counting. So for example, if you had, 4 apples on your desk, you're not going to do any type of scientific measurement to figure out how many apples you have on your desk. You're just going to simply go, I got 1, 2, 3, 4 apples on the desk and count them. So for example, the 9 pencils. So what exact numbers mean is that they can have an infinite number of significant figures. So you could technically make them any amount of significant figures you want. Where this really comes into play is when we do calculations. If you come across an exact number in a calculation, you don't have to worry about it in terms of significant figures. And we'll talk more about that in just a second in terms of calculations. But that's essentially what it comes down to. But they can have an infinite amount of significant figures. You essentially can make them as many as you want. Now, earlier we talked about writing things in scientific notation and a couple of things why maybe we kept some zeros, why we got rid of some zeros. And as was mentioned earlier in a question, there may be only one way to really get a number to the right number of significant figures. So for example, if we look at this guy here, 300 written like this with the decimal there does have 3 significant figures. And when we write it in scientific notation, that would be 3.00 times 10 to the 2. Again, the 2 coming from 1 and 2 places coming that way. Now, when we write a number in scientific notation, this part of the number in scientific notation is always significant. So when we write 3.00 times 10 to the 2, this has still 3 significant figures. And when you go from decimal to scientific notation, you should never lose any significant figures along the way. You should always maintain the same sig figs as you go from one way to the next, which means if I wrote 500 like this with no decimal, this has 1 significant figure. So when I write scientific notation, it should be 5 times 10 to the 2. 1, 2, 1 significant figure. Yeah. So as you go back and forth, you shouldn't lose any zeros, significant figures. You shouldn't gain significant figures either. And so, for example, if we excuse me, wanted to write, what do we want to do there? Let's do, say we had 145 or 1450, and we wanted to write it in scientific notation, we would go 1, 2, and 3 places, and it should be 1.45 times 10 to the 3. Again, here we would drop the 0 in this case because it is not significant. Now, let's say we did want to write this in 3 significant figures, right? So if you want to write this in 3 significant figures and you did 145, that would be 3 significant figures, correct? The problem, though, with that is there is a very big difference between 1450 and 145, right? Although they are both 3 significant figures, if I owed you $1,450 and said, here's 3 sig figs, here's $145, you're probably not going to be happy with me. I don't imagine so much. So what we did here is we changed the meaning of this value. You never want to change the meaning of a value just to try to get it to the right number of sig figs. So in this particular case, the proper way, if you did want to sort of write it as 1.45 times 10 to the 3, it maintains 3 significant figures. It also maintains the meaning of it as well. So let's talk about rounding. Normal rounding rules apply that you're probably familiar with. If it's less than 5, we just kind of drop it. So if we were going to go to 2 significant figures, that brings us to here. Looking at the next number, which is a 4, we would drop it, gets us 5.6, which would be 2 significant figures. If it's above 5, we do round. So 2 sig figs would take us to the 6 here. We would look at the 8. We go up 1, brings us to 5.7, which is 2 significant figures. Here as well, we look at the 8 as our second sig fig. We look at the 6, which is above 5. So we would round to 3.9, which would be 2 significant figures. Now, when we do rounding, especially when we're doing calculations, several calculations in a row, we typically do not want to round till the very end. So one way you could do that is to do what they call a guard digit, which is 1 or 2 extra digits that you kind of carry in your calculation until you get to the end. And then at the end, you sort of clean it up to the right proper number of significant figures. So for example, after this, it says here, but you only need 3 sig figs, which would take you to here. Right? And what you would do is, again, keep an extra digit. In my practice, you might want to keep an extra couple digits. It might be a good idea as well, and not really round, because if you're doing multiple steps and you round at each individual step along the way, your answer will get further and further away from the actual correct number. And what you would do is keep maybe the 4 on your calculator. You might even want to keep all the numbers and just continue on with the calculation and then clean it up when it's all said and done. So again, here, if we do a bunch of calculations and we get this on your display and we want to go to 5 significant figures, what would be the result here? We got our not significant here. We would start counting here. That'll be 1, 2, 3, 4, 5 would be our 5th significant figure. And then we got our 0 there. So I'm looking at maybe D looks like the winner there. 0.023060. The little line indicates really where the significant figures should be in your calculation. You can continue it on. And again, you don't necessarily have to do that. Some people do that, some people don't. You could just keep track of it if you want, and then again, clean it up to the right number of significant figures when it's all said and done. Now, before we get into that, one last thing about rounding. Again, you don't want to do extreme rounding. So for example, if we have 13,333 and we wanted to round to 2 sig figs, why don't you take a second and write what you think it would be? So if you're going 2 sig figs, it does take you to here. So perhaps an option somebody wrote was 13. Maybe somebody wrote 13,000. Maybe somebody wrote 1.3 times 10 to the 4th. So out of these 3 here, this one is definitely not the right answer. Again, for what we were talking about earlier, although it is the right number of significant figures, there is a very big difference between 13 and 13,333. Again, if I owed you $13,000 and gave you 13 bucks, you're probably not going to be very happy with me again. Now, 13,000 is 2 significant figures, no decimal point written there, still 2 significant figures, still about the same amount. So maybe because I'm a nice guy, you know, you give me the $333 discount for being a teacher and, you know, you let me out of the room. If you write 1.3 times 10 to the 4, 1.3 is 2 significant figures in scientific notation. So either one of those are okay. So again, people sometimes go crazy with the rounding in an effort to get the right number of significant figures, and they do what I call extreme rounding. And again, you never want to change the actual meaning of the number when you do rounding. It needs to maintain basically what it is. So let's talk about what we do with significant figures and calculations. So there's really 2 kind of groups of calculations that we do. Let's come back. One is multiplying or dividing. When we multiply or divide, the answer that we should have the same number of significant figures as the number. I'll spit that out again. Let me try that again. So the answer that we should have the same number of significant figures as the number with the least number of significant figures. So when we look at this, as you can see on the bottom there, this has 4 significant figures. This has 2 significant figures. So again, on our calculator, we may get a bunch of numbers, but because this guy has only 2 significant figures, it's kind of like the worst measurement. So your answer is only as good as your worst measurement. And basically, we should end up with 7.4, which is 2 significant figures. So if you add, if you multiply or divide, you're looking at significant figures, and it should be the one with the least number of significant figures should be the same as your answer. Now, the other one that we do is adding and subtracting. And when we add and subtract, we're also looking at the least, but it's different. Here, we're actually looking at the least number of decimal places. So adding and subtracting, we're looking at decimal places, not significant figures. So this number here has 3 decimal places. This number here has 2 decimal places. That means when we do our answer, it actually should go to 2 decimal places. Now we're going to look at the 5 and we're going to round it to 31.28. 31.28 has 2 decimal places, but it has 4 significant figures. So 2 decimal places, but 4 significant figures. So multiplying, dividing, sig figs least is what your answer should have. Adding, subtracting, decimal places, least is what your answer should have with that one as well. Again, same idea here. Your worst measurement is basically what's going to determine how good of an overall measurement that you basically took. All right. Now, let's come back. For multiplication and division, the number of significant figures, it does matter, and you always want to give your answers to the correct number of significant figures. So if you're doing a multiple step calculation, like I said before, you want to keep track of your significant figures and then really clean it up to the end. You don't want to do a lot of rounding before then. If you did a whole bunch of processes together, like if you took 3.25 times 1.2 and divided it by 4, 4, 5, 6, 7, what you would most likely do first is the stuff in parentheses, and here we're multiplying. So when we do the top part, let's go way up here. When we do the top part of that, that is 3 significant figures and 2 significant figures, which means your answer should have 2 significant figures. On the bottom here, we have 2, 4, 5 sig figs. That means that the last thing that we're going to do is divide a number that technically has 2 significant figures by a number that has 5 significant figures, which means our answer should end up with 2 significant figures. If I did the top number, again, I probably would not round. When I took 3.25 times 1.2, I would keep in my head that it should be 2 significant figures, then divide it by 44, 55, 67, and then round it to 2 significant figures when it's at the end. Again, you want to avoid that rounding to the end. You do want to keep track of it. And again, you want to kind of follow normal orders of operation when you're doing it. Again, with addition and subtraction, that last digit there in the decimal is sort of your worst measurement. And we don't have to worry about too much of the guard digits. Again, if you want to do guard digits, it's fine. If you just want to, you don't have to put the little squiggly line. If you don't want to, you can put the numbers and just keep track of it. But again, don't do a lot of rounding until the very end. So here, if we did some adding here, since we're adding, we're going to be looking at, again, decimal places. So this is 2 decimal places. This guy is more than 2, that is 4. Which means regardless of what the number is, we should end up with 2 decimal places when it's all done. And again here, if we added it together, we got there 30, 34. So you got like 34.0198 if you're just going to add it together, I think. And since we should go to 2 decimal places, it should be here. And in this particular case here, we would most likely want to kind of round up there. And we should end up really with, if you were to give the answer at the end, it should be 34.02 milliliters really should be the answer. Keeping your guard digit there, it should be right here. Yeah. I guess, or a couple of digits. They kept a couple of guard digits. Again, should end up at this guy. But the final answer, when it's all said and done, should end up something like the guy there on the right. Question on that, or multiplying or dividing with significant figures, or adding and subtracting. So obviously you should always give the right number of significant figures when it's all said and done. And again, avoid rounding. If you want to keep a guard digit or so on your calculation, you can. If you want to indicate it with the line, you can. I don't care if you do it with the line or not the line. But again, as you're doing the calculations, just don't do a lot of rounding until the very end. Any questions on sig figs, how to count them, how to do calculations with them? Okay, so that should get us enough to get you through the lab here today. So let's talk a little bit about the lab before we watch the video here.